welcome to The Explainer. Today we are jumping into one of the weirdest but also one of the most powerful ideas in all of science, quantum entanglement. It's a concept that so deeply bothered Einstein, and yet it's the very foundation for technologies that are absolutely going to change our world.
And our whole story really kicks off with this famous, kind of dismissive phrase. It comes from Albert Einstein himself, who was just really troubled by a core idea in quantum mechanics. He thought it was so strange, so completely against all common sense, that the theory had to be missing something big.
You see, quantum mechanics has some seriously bizarre ideas, like superposition, where a particle can be in many states at once until you look at it. But the one that really got under Einstein's skin was entanglement. Imagine you have two particles that are linked, part of one system. If you measure something about one of them, you instantly know the state of its partner, even if they're on opposite sides of the universe.
So this whole puzzle got a formal name, the Einstein-Podolsky-Rosen paradox, or the EPR paradox for short. They laid it all out in a huge paper back in 1935. Einstein simply could not get on board with what the quantum math was saying about how reality works.
Okay, so the whole conflict really boils down to two of Einstein's deepest beliefs. First, locality, the idea that nothing can travel faster than the speed of light, so something you do here can't instantly affect something way over there. And second, realism, the belief that objects have definite properties whether we're looking at them or not. A ball is still red even when it's in a dark closet. Entanglement seemed to just throw both of those ideas right out the window, suggesting this weird, faster-than-light connection that just shouldn't be possible.
For decades, this was just a big debate for physicists to argue about over coffee. But the very first piece of real experimental evidence for entanglement came from a physicist whose incredible work was basically hidden in plain sight for over 70 years, the amazing Qianxiang Wu.
Get this. In a lab deep underneath Columbia University, Wu and her student were literally making their own antimatter. They smashed positrons and electrons together, which created pairs of photons. And by taking these unbelievably precise measurements, they saw that these photon pairs were perfectly correlated, just like the quantum theory said they would be. They had actually documented entanglement in action.
And just to put this into perspective for you, her experiment in 1949 happened a full 15 years before John Bell published his famous theorem, and more than 20 years before the experiments that would go on to win the Nobel Prize. She was light years ahead of the curve.
Now, what makes Wu's achievement even more mind-blowing are the obstacles she had to overcome. She was dealing with intense gender bias in a completely male-dominated world, and on top of that, anti-Asian discrimination that was so bad that Berkeley wouldn't even offer her a permanent job, even though she was a superstar in her field.
So Wu's pioneering work really set the stage. Now let's see how this debate moved from being this philosophical head-scratcher to a direct, testable experiment that was designed to settle the argument once and for all.
All right, so the journey from theory to a real-world test basically happened in three crucial steps. First, the EPR paradox posed the big question. Then, a physicist named John Bell came up with a brilliant mathematical test. Basically, he figured out the absolute maximum amount two particles could be correlated if Einstein's classical rules were right. If an experiment found a stronger correlation than that limit, well then, Einstein had to be wrong. And finally, a young physicist named John Clauser designed the very first experiment to actually run Bell's test.
And that was Clauser's whole motivation. He just happened to find Bell's paper in a library and decided he was going to run an experiment to prove Einstein was right all along. He just felt like Einstein's view of the universe made sense, and the quantum view was, well, muddy.
So in 1972, Clauser did his experiment, separating his entangled particles by about 10 feet. And the results, they were shocking. The particles were way more correlated than Bell's theorem said they could ever be in a classical, Einstein-style world. They had violated Bell's inequality. So, in a great twist, Clauser, the guy who set out to prove Einstein right, ended up being the one to prove him wrong. The spooky quantum world was real.
But Clauser's incredible experiment wasn't quite the final word. It had what physicists call loopholes. Potential little gaps in the experiment that could explain the results. Like, what if the particle detectors were secretly signaling to each other somehow? It was going to take two more physicists and decades of hard work to slam every single one of those loopholes shut. And this is where Alain Aspect and Anton Zeilinger enter the story. What they did was systematically and brilliantly refined Clauser's original experiment.
over and over. Each new experiment they designed was more clever and more rigorous than the last.
So, in the 80s, Aspect's team closed that locality loophole. They made their measurement choices so incredibly fast that there was no physical way a signal could travel between the particles. Then Zeilinger's group just took things to a whole new level, using way better detectors and stretching the distance to over 1 kilometer, and then eventually beaming entangled photons between Earth and a satellite 1,200 kilometers away. Incredible.
So in the end, when you put it all together, the work of Clauser, Aspect, and Zeilinger, all of it standing on the foundation of Bell's theory and Wu's early experiment, they gave us irrefutable proof. Spooky action at a distance isn't some flaw in the theory, it's a fundamental feature of our universe.
Okay, I know what you might be thinking. This all sounds incredibly abstract, right? Just some weird quirk of the subatomic world. So why does it matter? Why should you care about this deep cosmic connection? Well, because it's about to change everything. See, entanglement isn't just a fun fact. It's the engine that's going to power the next technological revolution. It's the key to building quantum computers that can solve problems our best supercomputers today couldn't crack in 1 billion years. It's how we're building quantum cryptography, creating communication that is physically, by the laws of nature, unhackable. It even makes quantum teleportation of information, not people, a reality.
And the implications could go even deeper than that. There are some really out there but fascinating theories that suggest quantum things like entanglement might actually be happening inside our own brains. The thinking is that it could help explain consciousness itself, how your brain takes all these different signals and weaves them into a single unified experience. Now, it's a bold idea for sure, but it just shows you how far-reaching this research could be.
And this really brings us full circle. The story of entanglement is itself a story about, well, entanglement. It's a web of connections stretching across decades and continents, from Einstein's big puzzle to Wu's forgotten breakthrough, all the way to the Nobel laureates who finally proved it all true. It's a beautiful reminder that our understanding of the universe, just like the universe itself, moves forward through connection.